My name is Davide, and I work in Red Hat as a software engineer in the networking services team, and also in the RHIVOS teams. So today we are going to talk about RHIVOS and how we are trying to refine the kernel kern stack for car environments. Yeah, uh, everybody knows RHEL. And as you probably know, we are trying to target the automotive world. And we are doing that by tailoring RHEL into a new, smaller Linux distribution that should be able to run automotive workloads. We are trying to achieve the ISO 26262 certification and to have it in a continuous way so that we can run safely AZB application and QM application on the same operating system, on the same chipset, on the same everything. Yeah, networking is different in a car environment than what we are used to in a data center. This is a good thing. But indeed, in car environments, we still have networking components that exchange data. We have containers. We have so regular TCP, UDP, and IDP, IP protocols. We have applications that open sockets, Unix domain sockets or packet sockets. And we have hardware. So we need to provide support for Ethernet devices that do time-sensitive networking. And we have CAN controllers, and we need to pass data and transmit, receive data over that. So in traditional RHEL, we used to rely on a lot of debug tools. They're designed for container environments, for cloud, for places where you have a network administrator. There's no network administrator in a car. Yet we want to debug stuff well. And we want to do extensive testings like those that we have for RHEL. And last but not least, we have a lot of configuration tools that users can have. Probably many of you know Network Manager. Many of you know NM State. We want to leverage on those things also for car environment. Yeah. So this is the agenda for today. Very briefly, we will overview how to improve observability and debugability for the CAN software stack. We will overview how to extend the current testing. We will see how we can configure and document better the whole stack. There are other stuff on the way. If you are interested, just join us in the hallway track. And now I'm leaving the floor to Filippo.
Thank you. My name is Filippo, and I work in Red Hat as a quality engineer for the automotive kernel team. So lately, I'm also working on observability and debugability of the kern stack. And so let's talk about frame drops. So packet, we don't want packet to be dropped, but it happens. And when it happens, we would like to understand why it happens. So for this reason, adding the drop reason on the SKB comes in handy because it can help us to track the number of the drop frame and the reason why it happens. And so, for example, in this case, we just need to add on the trace point for K3 SKB an additional message that just tells you why a frame is dropped. Another topic is diag modules for CAN stack. So diag modules are used to retrieve information from the user space using netlink messages about the open sockets. And right now, Khan doesn't have a diag modules yet. And by defining it, we are able to let the user space have information about the number of Khan sockets opened and which virtual or physical device the socket is bound to, the ID of the process that owns the socket, transport protocol that are built on top of CAN. So is the socket an ISO-TP, RHO, or J1939? And as consequence, the type of the socket that can be SOC-RHO or SOC-DGRAM. The tool that is typically used to that leverage the diag modules is SS of IP root. And it basically works with almost every family, address family right now, even though it's pretty famous to be used with TCP or UDP, but it also supports safe packet, safe SOC, but not safe CAN, because we don't have the CAN diag module yet in the kernel. So right now, in this slide, I just want to show what we're able to achieve with an incomplete CAN socket diag modules. Luckily for us, apparently SSS still have the character C free to use. So we want to use it to also list information about the sockets that are opened. And so let Felix talk right now.
All right. So I'm going to talk a bit about testing. I'm Felix. I'm a software engineer at Red Hat. So one important thing if we want to make CAN ready for a car is that we get good testing for it. We want that stuff to work all the time. We want it to work in a way that we intended it to work. And one important step on that way is so-called self-tests, K-self-tests. K-self-tests are what we use in the kernel land for testing. So they are small programs where we basically test kernel features. You run that program on your machine. It's not like from the outside. You run it within your operating system. For a lot of subsystems in the kernel, we already have good K-self-tests. The newer the subsystem, the better usually the self-tests are. But for CAN, we didn't have any self-tests so far. There were some tests across the internet, but not like a central place where all of them ended up to be. So what we started taking over all these self-tests into Linux, into the upstream kernel, so they are close to the kernel, so they are attached to a kernel version. So when you upgrade your kernel to a new version, or when the new version is worked on upstream, self-tests are added for that kernel version. So it's really like binding the self-tests closely to the kernel. The advantage of having self-tests or K-self-tests for CAN is that in the Linux kernel world, we are used to those self-tests, and they run in almost all CI systems. So whenever there is a CI system, is it within Red Hat or is it within other companies, most of them run K-self-tests, and if you add new K-self-tests, they will run there mostly automatically. Sometimes you have to flip a switch, but it's a simple switch. It's not you have to build a new test environment or anything. And usually the advantage is that we can run them on virtual machines, so we don't rely on hardware. You don't have to have a CAN setup on your desk to test those ones. You can just run a virtual machine. So what we are doing in these self-tests, we are setting up small-ish CAN components with virtual CAN interfaces, which we luckily have, and we use those ones to resemble these like things that we see in the real world and test all the functionality that we want. That's one part of it. On the other hand, we also propped up these self-tests to be able to use them with hardware. So we can use our self-tests that are actually made for virtual interfaces, but also we can use them on hardware interfaces, because in the real world, we will end up with hardware. Like nobody needs virtual CAN interfaces, we need hardware interfaces in the end. Yeah, and we started that journey just now, but there will be a lot to come there and a lot of self-tests to be added, either for existing functionality where tests exist, or for new functionality where we want new tests. And with that, I hand it back to Davide.
Yeah, thank you. So yeah, last item for today is configuration and documentation. Yeah, configuration matters a lot. but for automotive, documentation matters a lot. So everything in the CAN stack, almost everything, is configurable through Netlink. One good thing that the networking standard most used protocol have is YNL. So there's the possibility to specify the Netlink API and the UAPI using a sort of YAML spec, and have all the headers and all the UAPI regenerated by a tool, rather than writing it manually. The good thing is also you don't need to rebuild the tool to include new features. So there's no need to rebuild IP route 2. Once a new feature is there with the kernel, it's already testable, just because we have the data model correctly set up. And of course, the data model is shipped in the kernel doc RPM as a YAML spec. So once you upgrade the kernel, you are just good to use the new stuff. Yeah, something like this is an example. Just update the RT-Link YAML spec in the kernel, and you will be able to, in the future, to use YNL CLI to just set the bitrate for the CAN0 interface, and that's it. And similarly, what you can do is to, whether you have this enum in the kernel UAPI, you can just rewrite it as an RT-Link YAML file and have it regenerated by YNL gen. The advantage, the enum is the same, so we don't break user space. We keep the promise. But yeah, the kdoc improves a lot. So this kdoc is not parsed on the left part. On the right part, you see the kdoc is automatically generated, and it can be visible as soon as it's just upgraded in the spec. We have been fast, low latency. We have 2 minutes left. And any questions, if you have them, we will be happy to answer. And then on the hallway track. One question? Chris? Yes. So the question is, how can you please explain how to set up a vCAN device? This is entirely done through the RT Netlink API. You can do it also today using IP route, and you just do IP link add name CAN0 type vCAN, and you're done. For the YNL command, stay tuned. One other question? So the question is, everything is upstream already, everything's ready? The answer is yes, no. Because we are sending KSL tests are already onboarded. Only as an infrastructure, we are going to incrementally onboard new tests. The drop reasons are currently in review in NetDev, and we will add more drop reasons. With regards to the diag module, the diag module will be sent to NetDev in the next days. So stay tuned. We are out of time. So thank you for listening, and thank you for being there.